Welcome back to our second Chapter 9 video. In the last video, we reviewed some of the reaction types that will be important for understanding cellular respiration. We talked about the way that electrons will be pulled from carbon and taken in the form of NADH to the electron transport chain. So the next part, we'll be starting to get into the actual specific reactions of cellular respiration, beginning with glycolysis. So glycolysis, of course, is going to happen in the cytosol of eukaryotic cells. So important to keep straight where exactly this happens. So glycolysis, all of the steps that we're about to look at will definitively take place in the cytosol. In our next video, we'll be starting to talk about these later things that will happen in the mitochondrion. For now, everything that we're about to talk about, you can imagine happening next door to a mitochondrion, but not inside it. So, as we discussed in our previous video, while the net reaction for cellular respiration is essentially the oxidation of carbon, this process is going to be broken up into many smaller reactions. So glycolysis, which is all we'll talk about in this video, you can see broken up into 10 steps. So this is going to be really broken up, but remember that this is going to help cushion that fall, these electrons going to oxygen, kind of cushion that fall in free energy. So that's why we need to have all of these steps so we can actually control the release of energy and collect it as chemical energy, ultimately to make ATP. So just like the last video, we can expect the reactions of glycolysis to fall into more or less one of three categories. Maybe some of them overlap a bit too. So we'll definitively see a redox step. This is going to be where electrons will fully leave carbon. So carbon, at the end of the day, is always going to be oxidized in cellular respiration. So we're going to ultimately see electrons leave the system. So we'll know where these steps happen. A very, very obvious indicator is going to be where NADH is formed. So anytime an NADH is made and leaves glycolysis, that is going to be where we've actually taken electrons. Those we'll save for later, but it's important to keep track. The second category, phosphate transfer, this is going to be kind of really just relegated to ATP. So remember that ATP is adenosine triphosphate. We'll either see ATP be used, so converting a TP to a DP and using one of those phosphates, or we'll create ATP. So that's where we're going to be looking at phosphate transfer. The last category is going to be rearrangements. These will be steps that will still sometimes be coupled with a redox or a phosphate transfer. We'll always see some rearrangements kind of happen, but when we don't use or gain any redox potential, we don't use or gain any ATP, we don't see either of those in that reaction, sometimes we just need to rearrange these molecules so that they can continue further through the process. So we'll just see some rearrangements happen kind of by themselves without using or creating ATP or gaining any NADH. So they're just kind of there to help us move down these free energy stairs so that we can get to the final product. So as I mentioned, glycolysis is broken down into 10 reactions, so 10 steps, and steps 1 through 5 are going to be referred to as the energy investment phase. So we are going to have to pay in a little bit before we can start to get the results. So you can kind of think about this in two ways. One, just looking at these reactions, and we'll get into the fine details of these in a moment, you can see that we're using ATP. So we've got a couple of phases, phosphate transfer, ATP being used, synonymous with using energy. So it's going to be steps 1 through 5. We can also see this in terms of the free energy. You can actually see kind of an ascending free energy, so we're having to go up in free energy for the first 5 steps. And that's kind of like that little uphill before we get to go down and use that momentum in a roller coaster. We've got to go up just a little bit before we can go back down. So the first 5 steps are going to be the energy investment phase. Okay, so we'll get started with some of these reactions, but thinking about the idea that everything starts with glucose. So glucose is going to enter into glycolysis. It will be processed through a series of reactions. I've only shown the first 5 here. We're still in the energy investment phase. But just so that we know what we're looking at, we're going to have glucose enter. Here we have the name of the enzymes that will catalyze these reactions. So glucose catalyzed by hexokinase. We'll get to our next product. You can see our second enzyme so that you know how these are laid out. So we can go ahead and start with glucose. So here's, again, a molecule of glucose. It has 6 carbons, which hopefully we're familiar with. So 1, 2, 3, 4, 5, 6. Okay. It will be important not to keep track of exactly which carbon is where at all times, but just the idea that we started with 6 carbons. Each of these carbons will need to be oxidized. That's where we'll see them leave as 6 carbon dioxides. So we won't actually see any of this carbon dioxide made in glycolysis. That'll be a little bit further, but keep in mind that we're going to be moving closer and closer to that point as we progress through glycolysis. So over the course of these 10 steps, I'm only showing the first 5 here, plus our pyruvate processing and the citric acid cycle, we're going to eventually see all 6 of these guys leave. Okay, so I'll give you guys some time to explore some of these steps 1 through 3 in your pre-lecture assignment. Okay, you can see there's a lot of these characteristics I've talked about here, this phosphate transfer, some rearrangements. Okay, but I want to take a little time and specifically address what's going on in steps 4 and 5. If you want to complete the questions related to these earlier steps before you watch this part of the video, that's perfectly fine. I just felt like this part maybe needed a little bit more in-depth explanation. So let's go ahead and look at steps 4 and 5 for just a moment. So now we're just zoomed in. Okay, so it's important to note this molecule, fructose 1,6-bisphosphate, okay, it looks like it has less carbon, but check it out. 1, 2, 3, 4, 5, 6. We still have 6 carbons. Okay, so we're just gone through some phosphate transfers, some rearrangements, just as you know you should have been kind of thinking about. 6 carbons. We're going to split this 6 carbon molecule, so this is catalyzed by aldolase. Okay, we're going to split this into 2 3 carbon molecules. Okay, so 6 carbons, 1, 2, 3, 4, 5, 6. Split it in half. We now have 1, 2, 3, 1, 2, 3. Okay, so we've split this into 2 3 carbon molecules. For whatever evolutionary biochemical reason, however, only one of these 3 carbon molecules is acceptable to continue in this process. So that is G3P, glyceraldehyde 3-phosphate. So the second product created, dihydroxyacetone phosphate, aka DHAP. DHAP, as is, cannot be further processed in glycolysis. The enzyme that will handle glyceraldehyde 3-phosphate in step 6, not interested in DHAP at all. Therefore, isomerase will convert DHAP to G3P. A lot of books show this as being reversible, and technically this is reversible. However, because we're continuously pulling from the pool of G3P, G3P can continue on through the process. We are going to be depleting the product end of this and therefore pushing the reaction basically only in one direction. So think of this as we split this. DHAP is converted to G3P. We have now two G3P molecules which can both continue on to step 6. So in that way, all 6 carbons can now move forward. So I'm going to show step 6 just so that you can see what I mean and how your book handles the nomenclature for this. Okay, but think of everything moving forward. DHAP has to be converted to G3P first. Okay, so G3P, we can now imagine we have 2 of those. Okay, and so your book is now going to put this little 2 next to your picture so that we are keeping track. We only have to look at one of these molecules, but there are actually 2 in play per glucose. So there'll be 2 1,3-bisphosphoglycerates, but we're only looking at 1 for simplicity. Okay, so you can see this is reaction 6. This is actually the energy payoff phase, but I think it's important just to see where everything's going to go. So our G3P will be converted, both molecules, to 2 separate molecules, 1,3-bisphosphoglycerate. So this is actually an interesting reaction to kind of land on as well. Hopefully your eyes are becoming like really attuned to this NADH. Okay, so yes, this is a redox step. We've collected 2 of them per glucose. Another thing I want to note is that this enzyme, triose phosphate dehydrogenase, is also, I think, maybe even more commonly referred to as glyceraldehyde 3-phosphate, just like this molecule, glyceraldehyde 3-phosphate dehydrogenase, or GAPDH. Okay, so you can also see it referred to as GAPDH or glyceraldehyde 3-phosphate dehydrogenase. So this is an alternate name. Okay, just so that you're comfortable with that, seeing it. Okay, so note that now the 6 carbons from glucose are split, and there are now 2 3-carbon compounds. Okay, in play here, noted at the side, noted here, this NADH. Okay, so we know that those NADH will be saved for later. And you can imagine everything from step 6 onward, it's happening twice to complete 1 glucose, but we're really only looking at just 1 at a time. Okay, and just because I think it makes it a little easier to remember, you can think of the enzyme, GAPDH, glyceraldehyde 3-phosphate dehydrogenase. Not interested in DHAP, but G3P, understandable. Okay, so yeah, I did probably mix some memes there, but that made it better, I feel. So you'll have, again, some time to go through steps 7 through 10 as you work through your pre-lecture material. But just to kind of recap, we talked about the first 5 steps being the energy investment phase. We used 2 ATP there. I kind of pointed them out, but you'll have, again, some time to explore that. Steps 6 through 10 are going to be the energy payoff phase. We already saw one of those payoffs in step 6. Okay, a little bit of foreshadowing, a prequel kind of deal, as these 2 NADH that we're going to be collecting here. All right, if you look further down, step 7 through 10, you can see that we're going to be collecting some ATP, 2 per glucose, okay, 2 per glucose here as well, for a total, which will give us a net per glucose. We'll end up getting 2 pyruvate, which is going to be our last product, 2 ATP net, okay, so 4 minus 2, and 2 NADH, which we've got here. Obviously, the protons, we talked about the mechanics of NAD plus NADH in the previous video. I'm kind of disregarding the protons for now. They will become important later, but mostly the electrons, okay? So always keeping track of where those electrons are going. Here's our some right now on NADH. ATP, we can add that to our bonus prize to our ATP pool later. Pyruvate is actually a really important molecule. It's going to carry a lot of the potential energy so that we can continue to oxidize those carbons and pull electrons off. So we're really going to be seeing a major electron payoff happening in the subsequent steps. So again, you'll have some time to explore the specific steps of glycolysis on your own, to look at some of the steps on your own, but hopefully this will help you guys see some of the really important concepts that are going to be present in glycolysis and give you an idea of what you'll need to look for. So in the next video, we're going to be looking at pyruvate processing and the citric acid cycle.